Welcome to the Spatial Modeling and Visualization with R INLA course. I said this morning, I'm Paula Moraga, and I'm an assistant professor of statistics at the King Abdullah University of Science and Technology, known as KAUST in Saudi Arabia, and the principal investigator of the Geospatial Statistics and Health Surveillance Research Group. My research focuses on the development of statistical methods and computational tools for geospatial data analysis and health surveillance, including methods to understand the spatial and spatiotemporal patterns of diseases such as malaria in Africa, leptospirosis in Brazil, and cancer in Australia. I've also developed a number of R packages for Bayesian disease mapping, detection of clusters, and risk assessment of travel-related spread of disease. And I'm the author of the book, Geospatial Health Data, Modeling and Visualization with R INLA and Shiny. The content of the tutorial that I'm going to give today is based on this book. This book is published by CRC, and it's also freely available at this URL. And it covers how to manipulate and transform spatial data and how to create maps using R, how to feed and interpret Bayesian spatial and spatiotemporal models using INLA and SPDE, and how to create interactive visualizations, reproducible reports, dashboards, and Shiny web applications to communicate information. The book is focused on disease mapping examples, but the methods covered are useful to analyze georeferenced data and many other disciplines that use georeferenced data, such as ecology or criminology. Okay, so today we are going to learn how to develop and interpret spatial models using INLA, and how to create maps and other visualizations to communicate results. The course is hands-on with 3 parts. In the first part, I will introduce geospatial data and the R INLA package. And then we will go through 2 examples showing how to model areal and geostatistical data. For the areal data, we're going to see how to estimate lung cancer risk in Pennsylvania in the USA. And for the geostatistical data, I'm going to show how to predict malaria prevalence in the Gambia. And again, these are disease mapping applications, but the methods can be applied in other contexts, for example, in ecology to predict the species distributions, and environment to estimate air pollution, or in criminology to assess patterns of crime. These are the packages that you need. These packages, you can install them from CRAN. And then INLA is not on CRAN, so you need to install it in this way, specifying the repository. Okay, so let's start. So who has seen this map before? Okay, a few of you. So for those who haven't seen the map, this is a John Snow map of cholera in London in 1854. So in that year, there was an outbreak of cholera in London, and people didn't know how it occurred, because they didn't know how cholera was transmitted. They thought that it was something bad in the air, but they really didn't know. So Dr. John Snow mapped the deaths, and he found out that all deaths were clustered around a water pump in Broad Street. So he convinced the authorities to remove the water pump, and when they did that, the outbreak disappeared. So this is one of the first examples of the importance of geospatial methods for disease surveillance. These methods can be useful to understand geographic and temporal patterns, highlight high-risk areas, detect clusters, measure inequalities, early detection of outbreaks. The results can be communicated using maps and other visualizations, and can guide decision makers to better allocate limited resources and to design strategies for disease prevention and control. And as I said many times already, these methods are also useful in other disciplines. Spatial data can be categorized in 3 types: areal data, geostatistical data, and point patterns. In areal data, we have the region of study partitioned in several sub-areas. And in each of the areas, we know the number of cases, the population at risk, environmental covariates, demographical covariates, and our objective is to estimate the disease risk in each of these small areas. In geostatistical data, we assume that the risk is a spatially continuous process that we can measure at specific locations. For example, here, these points represent prevalence of lymphatic filariasis in sub-Saharan Africa. So here we can see that in Ethiopia, there is lower prevalence. In pockets in the West, there is a higher prevalence, but we don't know anything in areas that are not sampled. So with geostatistical data, the objective is to predict what is the risk of the disease in areas where we don't have data. And then in point patterns, the data are the locations of the people with the disease. So here, this is the city of Valencia in Spain, and the dots are the locations of the people with kidney disease. So this is the same as here, where the dots are the locations of people that died from cholera. And the objective here is to understand what is the process that originates this data. Is this data clustered? Is it at random? Are these points close to a contamination source? So do you understand the difference between the 3 types? Do you have any question? Yes. Network data, what do you mean? Like trajectories of like people moving. Yes, so that would be another type of spatial data. Yes, like, yes, imagine that you have population flows that go from one location to another location, and we will use different methods to analyze this type of data. But historically, this has been the 3 types, but I agree with you that now we are producing more data in different formats, and network or population flows or trajectory data will be another type. Okay, so imagine we have aerial data and we want to estimate the risk of the disease in each of these areas. So one easy way to do it is to calculate the standardized mortality ratio, or SMR. And this is the number of cases observed divided the number of cases expected. So if we have the same number of cases observed as expected, SMR is equal to 1. If we have more cases observed than expected, SMR is greater than 1, and the area is high risk area. And if we have less cases observed than expected, SMR is less than 1, and we have a low risk area. So this is very easy to calculate, but this has some limitations because this may be misleading in areas with small populations or rare diseases. So imagine, for example, we have a municipality with very few people, and we have 0 cases. We will say that the risk is 0, which is not true. Or maybe if we have 1 or 2 cases, we will be dividing by a very small number, and we will get very extreme estimates of risk. So this is very misleading, and instead of doing this, we fit models that enable to incorporate covariates and to borrow information from neighboring areas to obtain smooth relative risks. So we use models like this. So here, theta I is the relative risk of area I. So is the quantity that we want to estimate. And we say that the number of cases in area I follows a Poisson distribution with mean the expected counts times the risk. And then we say that the logarithm of the risk is equal to some covariates plus random effect. Okay, so we put a fixed effects part to quantify the effects of the covariates on the disease risk. And then we put random effects to model variability that cannot be explained by the covariates. Yes? How can we calculate the expected, you say? Okay. Okay, later I will show you how to calculate the expected counts. A Poisson distribution is because we have a number, like we have 0, 1, 2, 3, and to model this type of data, we use a Poisson distribution. So it's like we have several distributions. For example, Gaussian distribution is for any quantity between minus infinity to infinity. Poisson is for integer numbers. Binomial is for 0 if the variable is 0, 1. Yes. Sorry, I don't. Yes. Yes, it's because I have internet. Yes. Okay. So here this is the model, and we can put covariates and random effects. And for the random effects, for example, we can include a spatial random effect to recognize that areas that are close to each other have similar risk, like neighbors have similar risk. And also an unstructured random effect to acknowledge that it's possible that two areas are very close to each other, but the risk is independent. So that's a possibility. Then in geostatistical data, we have measure disease risk at specific locations, and we want to predict a spatially continuous surface of disease risk. And we can use a model like this. So imagine that at each of these locations, we went and made a survey. So we recruited NI people. We did a test for the disease, and some people were positive and some people were negative for the disease. So we can model this with this model. So here the prevalence, PXI, is the prevalence at location XI. So it's the proportion of people in the sample that were positive. And NI is the total number of people in the sample. So here we have that the number of people that tested positive follows a binomial distribution with parameters NI, the total number of people in the sample, and PXI, that is the prevalence, the probability of being positive. And then we can say that the logit of the prevalence is equal to some covariates plus random effects. And the same, we can include covariates based on characteristics known to affect disease transmission, temperature, precipitation, vegetation, and so on. And then random effects to account for variation that is not included in the covariates. So maybe the covariates that we include here are not enough, or we didn't measure the covariates that we needed to explain the prevalence. And there will be other factors that we don't know about, and this will be modeled with the random effects. Any question? Okay, later we will see an example. And finally, point patterns. What I said, we have the data are the locations of the people with the disease, and we are interested in learning what is the process that originates this data.
I have a question on the previous slide. So geostatistical models are models of continuous phenomena, right?
Yes. Yes. So
meaning you have to tell you everything of it. So it's the thing to look at is the fraction of person, right? So how do I understand that at a particular point location? How can I have fraction? Because there are no people at points. Right?
yes.
At most points there are no people at all.
Yeah,
so
but
how can it be a fraction?
so but you know that one location, even if nobody lives there, if you go and you live there, the environmental conditions are good to, for example, to malaria to exist. If you go there, maybe a mosquito will come and will bite you. Maybe nobody lives there, but people, if you go to that location that is nobody, maybe this is a high risk area because there are a lot of mosquitoes and the risk of having malaria in that area is high.
There's a risk anyway.
There is a risk anyway.
Right. Okay.
There will be, so here this is a simplification because I'm predicting in a spatially continuous surface, but maybe I need to mask rivers or areas that, because here I am assuming that everything, like you said, is like the risk exists everywhere, but maybe there are locations like lakes that there is no risk.
Okay.
Okay. Okay, so this is about coordinate reference systems. I'm sure all of you know this, but if someone is watching this online, coordinate reference systems can be geographic or projective. So the Earth is an ellipsoid, so we can identify any location on the Earth by giving the latitude and the longitude. Well, the latitude is the angle from the location to the equator, and the longitude is the angle from the location to the prime meridian, and is given in degrees. And then we can also project the Earth on a plane. And by doing that, we will do some type of distortion, like we will distort areas or angles or shapes, and there are different projections. One that is very common is Universal Transfer Mercator, UTM. And this projection divides the Earth in 60 zones. And we can identify any location in the Earth by giving the zone number, the hemisphere, north and south, and then the coordinates within the zone, easting and northing, that are given in meters. So when we are working with data, maybe we are working with geographic system or projective or UTM system. Okay, any question? Okay, so now about integrated nested Laplace approximation, INLA. So who has worked with INLA before? Okay, some of you. Who has? Yes, who used this? Who used INLA before? Okay, and who? Okay, doesn't matter.
That's why you're here.
Yes, yes. So INLA stands for Integrated Nested Laplace Approximation, and is a computational approach to perform approximate Bayesian inference in latent Gaussian models. And these are models that include a spatial and a spatiotemporal model.
Can you elaborate a bit what is nested and?
Yes, I will explain later what is latent Gaussian models. INLA, the advantage of INLA compared to MCMC is that it's very quick. So if we are interested in fitting many models and comparing many models, we can do this with INLA. Or if we are using large amounts of data. INLA works very well, and also for modeling spatial data. And we can use INLA in combination with the stochastic partial differential equation approach to analyze point level data. And there is a package called INLA to fit this model. This is the website of INLA. If you go here, you will see tutorials, books. There is also a forum where you can ask questions. Then this is my book, Geospatial Health Data. And this book, Advanced Spatial Modeling with the Stochastic Partial Differential Equations by Elias Krainsky et al., focuses on the SPVE method. And it's also freely available here at this URL. Okay, so INLA can fit latent Gaussian models. So, and these are models that have this form. You have observations that follow an exponential family. So these observations can be Gaussian, Poisson, binomial, and these observations follow a probability distribution that depends on parameters and on hyperparameters. Then the parameters X follow a Gaussian distribution with mean mu and precision matrix Q that depend on hyperparameters. And then the hyperparameters follow another distribution that doesn't need to be Gaussian. So if you specify a model with observations from an exponential family and parameters from a Gaussian family and hyperparameters of any family, you're fitting a latent Gaussian model. And then the linear predictor can be expressed as a sum of an intercept, covariates, and random effects. Okay, so this is the models that INLA can fit. Then to fit these models, INLA computes the posterior marginals for the latent Gaussian field X and the hyperparameters theta. And it expresses these posteriors as integrals of this. And the terms inside the integrals are approximated using Laplace approximations. And then these integrals can be done numerically, so they can be integrated numerically with respect to the hyperparameters. And this is why it's called integrated nested Laplace approximation. Okay, but you don't need to do this to use the package. And then once you have the posterior distribution of your parameter, you can compute quantities of interest like means and quantiles that you are interested in. Okay, so this is INLA. And then to install INLA, you need to use this syntax. And then this is how INLA works in R. And it's similar. If you have used the LM function in R, this is very similar. So you have a model like yi follows a normal distribution with mean eta I and variance sigma square. And then you say that eta I is equal to an intercept plus the effect of covariate x1 plus the effect of covariate x2 plus a random effect. And the random effect follows a Gaussian distribution with mean 0 and variance sigma square. So to fit this model, you need 3 steps. To write the formula, then call INLA, and then examine the results. Like to write the formula, you do it like in the LM function. You put the outcome, then tilde, then the intercept, but you don't need to put the intercept because by default there is an intercept. And then covariate x1 plus covariate x2 plus random effect. And to include random effects, you do it with the F function. And you need to put indices for the random effect and the model of the random effect. Then you call INLA by providing the formula, the family of the observations, and the data. And then once you have the results, you can see a summary, or you can post-process the results. Okay, we will see an example later. Do you have any question? Okay, so now we're going to see an example of aerial data. So as I said before, we have a region that is partitioned in several sub-areas, and we want to estimate disease risk in each area. We can calculate SMR, that is observed divided expected. For example, if in one area we observed 200 cases and we expected 100, the risk is greater than 1. This is a high risk area. If in another area we observed 100 cases and we expected 200, the risk is less than 1. So this is a low risk area. So to calculate the expected cases, we used this formula. So imagine that we are analyzing a disease that affects old people, for example, Alzheimer, and we have 2 municipalities with the same number of people. In one municipality, everybody is very old, and in another municipality, everybody is very young. So in the municipality with old people, we will expect more cases than in the municipality with young people. Okay, so to calculate the expected counts, we consider the population and we stratify by several factors. For example, age and sex. And this is the formula. So we need to calculate the rates in the whole population, like the standard population is the whole population, like this whole state. And we calculate the number of cases divided the population in the stratum J, in the standard population, and then we multiply by the number of people in area I of that strata. And then we sum for each of the strata. And this is the formula that we use. And this is to take into account that several different areas will have different age and gender structures, and we want to calculate the expected counts in each of them. Any question? Okay, so this is how we calculate SMR, observed divided expected. But if we have, we are going to do it in a better way, that is using a model. And we are going to use this model. So conditional on the relative risk in area I, the number of people with the disease follows a Poisson distribution, which means the expected counts times the risk. And then the logarithm of the risk is equal to some covariates plus random effects. And we can put a spatial random effect to model spatial variation and a structural random effect. Okay, so let's go to this tutorial and we're going to see an example. So if you type paulamoraga.com/tutorial aerial data, we're going to see this. Is everybody here? You know how to get here? I don't know how to do this. Okay, so here in this tutorial, we are going to estimate lung cancer risk in Pennsylvania, in each of the counties of Pennsylvania. And we are going to use data that are in the Spatial EPI package. The Spatial EPI package has the population, the lung cancer cases, and the smoking proportions in each of the counties. And we're going to calculate the SMR, and then we're going to feed a model with INLA, and we're going to visualize the results with leaflet. Okay, so first, you need to load the Spatial EPI package and attach the data PNLC, and you can see what's in there. So if you put $PNLC, you will see the contents of this data set. So take a moment to explore the data a little bit. Okay. Can you see the data? Okay, so if you see the data has for each county and its race, gender, and age. It has the number of cases and the population. So race can be white and non-white, gender can be female and male, and age can be under 40, 40 to 59, 60 to 69, and more than 70. And here, for example, we have County Adams, race non-white, gender female, and age under 40. There are 0 cases and 1,492 people living there. Okay? Any question? Okay, so this is the data. Then we also have an object that is smoking. And smoking gives the proportion of smokers in each of the counties. Like Adams, 23% of the people smoke. And then the data also have the map with the counties. And we are going to assign these spatial polygons to a variable called map. Okay. Do you have all of this? Do you have the map? Okay, so now we want to estimate so first we're going to calculate the standardized mortality ratio, SMR, in each of the counties. And this is the number of observed cases divided expected cases. So what do I need to do? Because I have the data, so for each of the counties, I have the number of cases by race, gender, and age. To calculate the total number of cases in each of the counties, what do I need to do? Okay, so what I'm going to do is to aggregate data by county. So for now, I only want the number of cases in each county. Like so since I have the number of, so I have, for example, in County Adams, I have 0 cases in this stratum, 0 cases in this stratum, 1 case in non-white, female, and 60 to 69. So I'm going to sum all of these cases for each of the counties, okay? So you can do it like you want. For example, you can use a group by of the dplyr package. You group by county, and then you sum the number of cases, and you get, in Adams, there are 55 cases, in Allegheny, 1,000 cases, or you can use the aggregate function by giving the cases and aggregating by county and then doing the sum. Okay, and if you do that, you will get for each of the counties the number of cases. Okay, now I'm going to calculate the expected cases. And we do this using indirect standardization, using this formula. So you can code this formula if you want, or in the Spatial EP package, there is a function that is called expected that we can use. And this function, we need to provide the population, the cases, and the number of strata. So how many strata do we have? We have 2 races, 2 genders, and 4 age groups. So we have 16 strata. And before calling this function, we need to order the data by county, race, gender, and age. So we first order the data, and then we call expected, and we get the number of expected cases. Like, for example, in Adams, there are 55 lung cancer cases, and we expected 69. So the risk is high or low? Is low, no? Because we have less cases than expected. Okay? And then we are going to use also smokers proportion, and we are going to merge the data with the smoking, and we are doing to do the merge by counting. Okay, and then to calculate the SMR, we do observed number of cases divided expected. And that's it. So we have, for each of the counties, number of observed cases, expected cases, smoking, and SMR. Okay, now we're going to do a map of the SMR values. And I'm going to use Leaflet, but you can use other packages. You can use map view or tmap or ggplot or the package that you like the most. So for doing that, I'm going to construct a spatial polygons data frame. So you can also do this with the SF package. But the time I wrote the tutorial, I think to do the leaflet map, I needed this package, and also I needed this object, and also to construct the neighbors matrix that I need later. But I think that now you can do it with the SF package. So you create a spatial polygons data frame, providing the map with the polygons, the data, and joining by counting. Okay, so now a map has the data. Is everybody here? And then you can plot the map. Who has used Leaflet before? Okay, so Leaflet is a JavaScript library for interactive visualization. And you can add different layers of data. You can add background maps. You can add markers, and it's very useful to see the data into context. The thing is that now there is another package that is called Map View that works very well. That there will be a session on Map View, and you can also use that because you will need less, because here we need to define the polygons, the legend, and with Map View, it will be easier to do it. But here we are going to use Leaflet. So we load Leaflet, and then what you need to do is we define a palette of colors like yellow, orange, red to map SMR. And we say we're going to add polygons. The border of the polygons, of the areas, is going to be gray. Weight is the width of the boundaries. Fill color is the color that we're going to put in the areas. Fill opacity 0.5 is to see the background of the map. And then we're going to add a legend here in the bottom right. Okay, and if you do this, you will see a map that you can zoom in, zoom out, and you can move. We can improve this map. For example, what we are going to do is to add labels. So when we hover the mouse over one of the areas, we will see the information of each of the counties, like the name, observed cases, expected cases, proportion of smokers, and SMR. And we can do that by defining some labels. Like here, you need to write HTML syntax. I'm going to plot a county, number of observed cases, number of expected cases, smoker proportion, and SMR. And then when I add the polygons, I'm going to say that when I hover the mouse, if an area is highlighted, I'm going to increase the border. I'm going to put a border of more weight equal 4. These are the labels, and here I have label options like the font, padding, like the distance between the border and the text size, and direction auto, because the labels can be shown in the left or in the right. Okay, is everybody here? Okay, so this is the map. So we have constructed a map that shows the standardized mortality ratio in Pennsylvania. And here we can see areas with very low SMR, these yellow areas, and areas with very high SMR. But as I said before, this has a limitation, is that if the population that lives in each of the counties is very low, we will get very misleading values. So instead of this, I'm going to use a model, and I'm going to fit this model. So I'm going to say that the risk in each of the areas is called theta I, and the number of observed cases is yi. And this follows a Poisson distribution, which means the expected counts times the risk. And then I'm going to say that the logarithm of the risk is equal to an intercept plus the effect of smoking, because we think that maybe smoking can explain part of the variability of the risk, and then random effects. And I'm going to put a spatial random effect that has this form. It's called conditionally autoregressive model, CAR. And this says that the random effect in one area I it follows a normal distribution, with mean the random effect in the neighborhood, like one area is neighbor from another area if they share a common boundary. And then the variance is inversely proportional to the number of neighbors. And then I'm going to put a random effect VI to model variability that is not explained by the covariate, but it's also variability that has no spatial structure. So I'm going to repeat. So I'm going to put smoking as a covariate, because we think that the smoking can explain lung cancer risk. But of course, there will be other factors that we haven't measured, we don't put in the model, and we are going to model those factors using random effects. I'm going to put a spatial random effect because it's possible that if two areas are close to each other, they have similar risk. And I'm also going to put an unstructured random effect because it's possible that even if two areas are close to each other, they are very different. Okay, so to fit this model, I need to compute the neighborhood matrix. So I'm going to say for each of the areas, what are the neighbors? And there is a function that is called poly2mb to do that. So if you pass the spatial polygons data frame map and you call poly2mb, you get the neighbor. So for example, area 1, the neighbors of area 1 are 21, 28, and 67. the neighbors of area 2 are 3, 4, 10, 63, 65, and so on. These are the neighbors. In INLA, you need the neighbors, but you need it in a different format. So once you have the neighbors, you need to call NB2 INLA to have the neighbors list in a format that can be read by INLA, and then you read INLA, you type INLA read graph, and now G has the neighbors of each of the areas. Any question? Okay, so now we're going to specify the formula. And we do this in a similar way as we do it in LM with the LM function. We put the outcome variable y, then tilde, then the intercept, but we don't put the intercept because by default there is an intercept, a smoking, and then two random effects. The spatial random effect and the unstructured random effect. The random effects are specified with the F function. And the first argument is the index that applies to each observation. So here I create the index for the U and V random effects. And this is just a vector of 1 until the number of areas that are 67. And then here I say that this model is BESAC, this is the spatial model, and this model is IID, this is a zero mean Gaussian model. This is the formula, and then I call INLA, and I call INLA by providing the formula, the family, so the data was Poisson, so I do Poisson. The data is here in map data. These are the expected counts. And then I say control predictor compute equal true, because later I want to compute the posterior means of the predictors. So, okay, I have the formula and I call INLA, and my result is in res. Is it clear? Okay, so these are the results, and now we can examine the results. So if we look at the fixed effects, we see, for example, that the posterior mean of the intercept of beta 0 is minus 0.3, and a 95% credible interval is between minus 0.6 and minus 0.02. And what is the effect of smoking on the risk of lung cancer? So if I look at the coefficient of smoking, beta 1, I see that the posterior mean is 1.15, so it's positive. So if the county has a high number of smokers, the risk of lung cancer is high. But then if I look at the 95% credible interval, this is minus 0.08 to 2.38. So this includes 0. So the effect of smoking is not significant. It's positive, but then looking at the uncertainty is not significant. Okay? And then if you are interested in plotting the posterior distribution of beta 1, you can also do that. Like here, what you need to do, the posterior distribution of the coefficient of smoking is here. Marginals fixed smoking. You can calculate this plot that shows the posterior distribution of beta 1. If you are interested in doing that. Okay. And now we're going to show the risk. So we're going to show the risk of lung cancer in each of the counties. That is this. So what is that? So in the result object, there is an object that is called summary fitted values. And here there are the estimates for each of the counties. We have the mean, and we also have two columns with the lower and upper limits of 95% credible intervals that are 0.025 quant and 0.975 quant. We're going to do this. In the object map, we're going to add a variable relative risk with the mean risk, a variable lower limit with the lower limit of the 95% credible interval, and a variable upper limit with the upper limit of a 95% credible interval. And then we can do the map again with leaflet. We specify a palette of colors, we write the labels, and now we also say the relative risk and the uncertainty interval. And then we put a background map, and we add polygons and the legend. And we get this map. And this is the risk. So we have estimated lung cancer risk in each of the counties in Pennsylvania. Here we can see that the risk is higher here in Philadelphia, is lower here in the center, and we also have a measure to quantify the uncertainty. So here, for example, in Philadelphia, the risk is 1.15 and the 95% credible interval is between 1.09 and 1.21. So it's a high risk area. Yes.
So is this caused by this covariate, or is this caused by this, these are?
It's a combination of both. So we have included a covariate that allows us to predict in each of the areas what is the risk, and then we have the spatial covariate to smooth the data. Like before, we had very different values, and now we have seen that by including the spatial random effect, there is the spatial components plays a big role, because we are observing that areas that are close to each other have a similar risk. But here in Philadelphia, for example, we are observing a very different risk from the rest. And we can also examine, if we look at the hyperparameters and the random effect, we can also plot the spatial random effect and the random effect for the unstructured component. And you can see each of those components. Okay, any question? So this is disease risk, but you can use it, for example, if you are looking at car accidents, you can see what is the risk of an accident in each of the areas, or any other variable that is a count variable. Okay?
For instance, somebody is living there for an X amount of generations.
I didn't listen. Can you repeat the question? If someone goes there to live for a temporary period of time? Yeah, the thing is that this is a very simple model, because when you do these maps, this is like I'm counting, I go to the registry of cancer and say, okay, how many people are in this area that have the disease? But maybe this is, these are people that, as you said, moved here recently, and they have cancer because they were exposed to some element that produced cancer in another location. So you will need models that account for the history of the population. So yes, because here we are observing in this point in time, in Philadelphia, the risk is very high, but maybe it's because the people that are living there come from other places where they were exposed. So very, very good point. Hmm. Yes, so here we have fitted the model using the total number of people in the county, but you can do also models at individual level and taking into account covariates at individual level with age and other exposures at that level. Hmm. Okay, so this was the modeling of aerial data, and now we are moving to modeling of geostatistical data. Okay, so this is when we have. So I say this is risk, but maybe if you are talking about air pollution, you can have air pollution that is a spatially continuous process that you can measure at a specific sites. So you can put monitoring stations to measure air pollution, and then you want to predict air pollution in other areas. So here is the same, but with disease risk. So in each of these points, we have done a survey. So we have recruited NI people and made a test to see if they were positive or negative for the disease. And then we do the ratio of number of positive divided the total number of people in the survey. And we get like some information in these locations where we did the surveys, but we don't know anything about areas that are not sampled. So we want to predict disease risk in areas that are not sampled. And this is very useful for decision makers to decide where to allocate the resources, which areas are more in risk, and like to invest more in those areas. And we're going to use this model, and this model says that conditional on the true prevalence at location xi, the number of people positive for the disease follows a binomial distribution with parameters ni, that is the number of people in the survey, and the prevalence. And then the logit of the prevalence is equal to some covariates plus spatial random effect plus an independent random effect. So here, if you think about infectious diseases in low and middle income countries like malaria or dengue, all of these diseases are affected by environmental covariates like temperature, precipitation, vegetation. No? Maybe if a disease is transmitted by mosquitoes, and mosquitoes are close to water bodies or in vegetation areas, these covariates will help us to understand the risk in the areas, to predict the risk in the areas. Okay, so we have covariates, and then we include a spatial random process to model variability that is not explained in the covariates. Because again, I can think, okay, this disease is affected by temperature, precipitation, population density, and so on. But in addition to that, there are other factors that we don't know about, we didn't measure, we cannot measure, and this will be in the part of the random effect. And we can put a spatial random effect to acknowledge that locations that are close to each other have similar risk, and an independent random effect to acknowledge that locations, even if they are close to each other, have different risks. So to fit this type of models, we use the stochastic partial differential equation approach or SPDE. And this is implemented in INLA. So we have a continuous Gaussian random process, like a continuous surface. And what SPD does is to approximate the continuous process by a discrete Gaussian process using a triangulation of the region of a study. So imagine we have this data, these points, and we want to estimate a spatially continuous process. Instead of doing that, I'm going to estimate the process at the vertices of this triangulation. So I'm going to put a triangulation on top. The software will predict the process at the vertices, and then it will interpolate. Look, for example, imagine I have a location here, X, that is within this triangle, with vertices S1, S2, S3. So what SPD does is saying the value of the process at the location X is equal to the value of the process at the vertices with some weights. And the weights are given by the barycentric coordinates. So they are proportional to the area that form the point and the vertices. Like, for example, the value of the process at location X is equal to S1 multiplied by the area A1 divided the whole area plus S2 multiplied by the area A2 divided the whole area plus S3 multiplied by the area A3 divided the whole area. And this is how SPD works. It approximates the continuous process by a discrete process using this triangulation, and then it computes the value of the process at each of the locations using a weighted average of the value of the process at the vertices of the triangle. Okay, and for doing this, when we use INLA, we need to define a projection matrix. And this projection matrix maps the continuous Gaussian Markov random field from the observations to the triangulation nodes. So this is the matrix A. It has n rows and g columns. N is the number of observations we have, the number of points. And G is the number of vertices of the triangulation. And each row has possibly 3 non-zero values at columns that represent the vertices of the triangle that contains the point. For example, if we have one observation that coincides with a vertex, and the vertex is vertex 1, we will have 1 here, and the rest of entries will be 0. If we have an observation that is in one vertex in position 3, we will have one here in the third position and the rest 0. And then if we have an observation like here that lies within one of the triangles, all the elements of the row will be 0 except 3 of them that will be the positions of these vertices, S1, S2, and S3. And there will be the weights, these weights, A1 divided A, and so on. Okay, so this is the projection matrix that we need to calculate in INLA, in SPD. Okay, and now we're going to see a tutorial. So you can go to this tutorial geostatistical data. Okay, so here we're going to predict malaria prevalence in the Gambia, in Africa, using data that are in the GeoR package. and also using environmental covariates that we can download with the raster package. And then we will predict malaria using INLA, and then we will visualize the results with leaflet. So if you load the GOR package, data are here in Gambia, and it contains like malaria prevalence in children. Like there are 2,000 children that live in 65 villages, and for each of the children, for each of the child, we know if they are positive or negative for malaria. Like for example, in this location, X given by X and Y, there is a child that has malaria. And this is the age of the child in days. And these are other covariates related to net use, vegetation, and health centers. Then in this other location, there is a child that is negative for malaria. And this is the age in days and other information. Okay, so we have individual data, but for this example, we are going to aggregate the data, and instead of using information of children, we are going to work with villages, like the proportion of people with malaria in each of the villages. So to calculate the prevalence, so we have 2,000 children that live in 65 villages, and I'm going to calculate the proportion of children with malaria in each of those 65 villages. So we can do this, like we group by coordinates, and we calculate the total number of children, the positive, and then the prevalence is the positive divided total. Do you have any question? So here, for example, now we have a data set where we have for each of the villages, these are the coordinates. So for the first village, we have 33 people, 17 were positive for malaria, and the prevalence is 17 divided 33.5.
Children.
Yes, children. In the second village, we have 63 people or children. 19 were positive, and the prevalence is 19 divided 63. Okay, so we can try and plot this data, and again, you can plot it using the package you want. I'm going to use leaflet, and for using leaflet, I'm going to transform these UTM coordinates to longitude and latitude. Okay, I'm going to use this syntax. So Edzer told us yesterday that we don't need to use this projection string anymore. So I need to change this at some point. But so if you do it like this, you create a spatial points object with the UTM coordinates, and then you transform it to longitude and latitude. And now we have a data set with the UTM coordinates, total, positive, the prevalence, and these are the longitude and the latitude. And I do this because I'm going to use leaflet to plot them out. Okay? So, and again, so this is what we are going to obtain. So this is for each of the 65 villages, the prevalence. To do this math, you can define a palette of colors with breaks 0, 0.25, 0.5, 0.75, and 1. Then I'm going to add a background map with providers CARTODB positron because I want to distinguish the colors that I put here from the background map. Then I add circles with providing the longitude and the latitude and the color. Then I add a legend here. And then I add a scale bar here in the bottom left. Okay, so here we have seen, like, for example, in this area, we see surveys where the prevalence is higher, and here in the middle, there is a lower prevalence. And what we want to know is what is the risk of malaria, not only in the locations where we have surveys, but in the whole Gambia. Okay, to do that, I'm going to use a model, and I'm going to use a covariate that is elevation. And you can download this covariate with the raster package. If you put get data, and then you say altitude, and then country is the ISO code, and then mask equal true to set to true, like to set to NA the locations that are outside the country. And you can also plot elevation, so you can see what we downloaded. So this is elevation in the Gambia, and you can plot this using add raster image. Any question? Okay, so we have the prevalence, and we have a covariate, and now we're going to fit a model to predict malaria prevalence using this covariate. So in the data set, I'm going to add a column alt with the altitude, and I'm going to, the values can be extracted with the extract function. So this R is the raster of the altitude, and I want to extract the values at the locations given by the longitude and the latitude. And now this is the data set. For each of the villages, I have the total number of people tested, the people that tested positive, the prevalence, and the altitude. Okay, so this is the model, conditional on the true prevalence. The number of people that tested positive follows a binomial distribution with parameters Ni, that is the number of people in the survey, and Pxi, that is the prevalence. And then I say that the log of the prevalence is equal to an intercept plus the effect of altitude plus a spatial random effect. The spatial random effect is a zero mean Gaussian process with a given covariance structure. One very, well, the covariance structure that is implemented in INLA is the Matern covariance function, and it's very flexible. Like here, this is the form that it has, but here what you need to know is that there are several parameters, like sigma squared is the variance, and then the parameter kappa is related to the range, and the range is the distance at which the spatial correlation is close to 0. So when you fit the spatial process to model residual spatial variation, this process will be different in different applications, and the range is the distance at which two different locations, the correlation is 0, so they don't have anything, they are not related. Okay, so this is a spatial continuous process, but in INLA, we approximate the spatially continuous process with a discrete process using a triangulation. And we're going to use this triangulation or mesh. So the red points are the locations. And then we need to put a triangulation on top to do the approximation. So the triangulation has an extension, so it has small triangles, because the smaller the triangles, the better is the approximation. And we also need to add an extension, because when the package fits this model, we want to avoid boundary effects. So if we don't put this extension, the variance in the borders will be increased. So we need to put this extension. So to construct the triangulation, there is a function that is called INLA mesh 2D, and you provide the locations, COO, and then you provide the maximum allowed triangle edge lengths in the region and in the extension. And then you can also add a value, a cutoff value, to avoid building many small triangles where we have very close points. Okay, so this is the triangulation, and we see that there are 669 vertices. Okay, now we're going to do we're going to apply several functions to obtain the data that we are going to pass to the INLA function. So at the beginning, if this is the first time you see this, it may seem a little bit complicated, but then in other applications, it will be the same. Like, it's always the same. You need to follow these steps, and that's it. So you need to construct an SPD object using INLA SPD to matter, and you provide the mesh, and alpha is equal to 2 because we are working in the spatial case. Then we need to construct the indices of the spatial effect that are constructed with this function, INLA SPD make index. And then we need to construct the projection matrix. So this is the matrix that maps the observations to the triangulation nodes. And to do that, you just need to call this function by providing the mesh and the locations. Okay, so this is the data and the objects that you need to estimate the process. And now we are going to say where we want to predict. So which locations we want to predict. You can do this like you want. Like what I did was saying that I want to predict at the locations that are given in the raster of the elevation. So R has the raster of elevation that I downloaded earlier. If I do raster 2 points, I will get the coordinates. There are 12,000 points. I can also, instead of predicting in 12,000 points, I can also predict in a fewer number of points. For example, I can aggregate the raster using a factor of 5, and I can, instead of 12,000, I can predict in 627 points. And then that's it. So these are the locations where I want to predict. And these are COOP. And then I also need a projection matrix that projects the process from the prediction locations to the vertices of the triangulation. Okay, so I have everything now. I just need to construct stacks to call the INLA function. And I have a stack for estimation, and a stack for prediction, and a full stack with the stack for estimation and the prediction together. I put a tag here for estimation, I call it est, and for prediction, I call it pred, because later I want to retrieve elements of these stacks, and I want to know what are the labels. The data are this is the outcome, positive, the number of trials is total, these are the projection matrix, and these are the random effects, the intercept, the altitude, and the indices. And for predictions is the same, but in the outcome, I put NAs because I want to predict. And then I put the stack of estimation and prediction together. Okay, so I have already the data, and now I need to call in. The formula is this. This is Y is the number of positive, V0 is the intercept, covariate is the altitude, and this is the random effect that I specify with the F function. And then I call INLA, where I provide the formula. The family is binomial. The number of trials, this is the link is logged. The data is stack full. And then other options to compute the posterior marginals. And as I said before, if this is the first time you see it, it may seem a little bit complicated, but it's just a few steps that you need to follow, and that's it. You don't need to know what INLA is doing internally. You just do this, and that's it. Any question? Okay, so we have fitted the model. The result is here in res. And then if we do summary res, we can see the intercept and the effect of covariance. So here we include elevation. So we see that elevation reduces the effect of the risk of malaria. But here, if we look at the 95% credible interval, it includes zeros and it is not significant. And then we can plot malaria prevalence. So the predictions are in the object summary fitted values. The posterior mean is here in mean, and this is the lower and upper limits of 95% credible intervals. And to know what is the indices of the prediction, we can say, I want to know what are the indices for the tag prediction. And then we can put it here, index. So we have the mean and the lower and upper limits of the malaria prevalence. And then we can plot it as you want. Like here I convert it to a raster, and then I plot it with leaflet. So this is the prevalence of malaria in the Gambia, and we used in a real application we will use a finer resolution, and also here we have the river that we can mask the river, and this is the mean prevalence, and then you can also plot lower and upper limits of 95% credible intervals. Okay, any question?
So this lower and upper percent highly correlated with the density points.
The uncertainty you say? What is
the bottom of the lower, upper and lower?
Yes.
The location points.
Yes. Yeah, the thing is that like the triangulation I used was not very good, because I wanted to do it like, if you do it, you can get the results very quick. Also, I just used elevation. There will be other factors that affect malaria. So these predictions are not very good. It was just an example, but it's true. Like we will see that uncertainty is lower where we have more data. Yeah.
So the points just randomly chosen. I mean, that's
the points. So there are like studies that do randomized clinical trials and choose the points in the best way, but there are other applications where there are no points are chosen just looking at the literature to see who made this survey, and they put all the surveys together, but they don't follow any rule. So sometimes you have chosen the points in a good way to be able to represent all the areas, and sometimes you have points that are given to you, but they are not representative.
Okay. Well, yeah, just it's visible and it's really strong. It's wrong in the sense, suboptimal.
Yes,
yes. You have the, different probability level of the upper lower confidence level just based on density points.
Yes.
If somebody will use this map, they will have an idea that the other place is the same.
Yeah, so I'm trying to go out here. Yes, so the thing is that, for example, in the map of lymphatic filariasis I showed,
So far, I see these models defined, we define formula. The idea is to keep it very simple. So just spatial technique, like just the one or two covariates.
yeah, so the thing is that this is not ideal. Like the thing is that here I also have altitude, one covariate, but in real applications you will have many more covariates. And also I'm including the covariates in a way that the covariate has a linear effect on the response. And this is not true. Like for example,
How does INLA claim to be like 500?
I have never tried.
Would it be very computational?
I have never tried, I don't know, because you will also need to check, I think, the correlation between your covariates. Okay. Yes, because maybe if they're correlated, they are not. It doesn't work. I'm not sure.
And the other thing is to take INLA and just do not simple INLA fast set, and then do subsetting, and then do ensemble out.
Yes, so you can predict and do the estimation part, and once you have your model, your predictions, you can predict in subsets. Like if you want to predict for the whole world, you can predict for Europe, then from America, and this will be much less computational intensive. Like you can fit once the model, only fit and then predict in separate processes.
Okay.
And here. Okay, so that was everything I wanted to say for modeling. Do you have any question? So if you want to do cross-validation, I don't know if you can do it in INLA. So you can do it yourself. You can split the data into sets, one for training, another for validation, and do the cross-validation yourself. I don't know if there is like an option that says do cross-validation for me. I don't think so. Yeah. Yeah, so you need to define the measure that you want to if you want to see the goodness of fit of your model in predicting, or you can also calculate, for example, 95% coverage intervals, and this is the proportion of times that your predictions, the proportion of times that the real data are within the 95% credible intervals. So the proportion of times your real data are in the uncertainty intervals that you estimated. So this is another way to incorporate uncertainty. Okay. There was another question.
because we basically approach a lot of changes forward so that you have point observation with big spatial needs.
So, so change for support, like, so the thing is that what you can do is, like, for example, if you you can fit the model and you get a spatially continuous process, and then if you want to obtain predictions in a different solution, you can use the spatial process and average in the areas that you want, in the support that you want. I don't understand the question.
Basically, when you have these point predictions, you just get a mean for a spatial block. Then you can see the information distribution of this spatial.
Ah, okay, yes, yes. So there is a function that is called, I don't know how it's called, but you can sample from the joint posterior, and then you can do the averages or the things you want. Okay.
Can you do spatial simulations?
What?
Like in geostatistics, you can do like a geostatistical simulation, so the simulation of the same spatial structure. Can you do that with INLA too?
Like you can define a model and then...
Yes, and then you simulate, let's say every pixel, let's say you still have the spatial structure, but you also have all the properties of distribution and everything.
I haven't done it, but maybe
simulations, and you average, you get exactly the prediction.
Yeah. So in INLA, what you get is the posterior distribution of your parameters, so you can draw samples from this posterior. So this is similar to simulation.
Just like a Monte Carlo, but
yes.
How do you keep the spatial structure?
Because you are also simulating from the spatial process, and the spatial process has a spatial structure. Yes.
The moment there's no function like that.
I haven't. I don't know. I don't know.
Okay.
Okay. So I have and this is again this is mapping, but if you want to estimate air pollution, for example, you can also do that. Here I have a few slides about interactive visualizations and dashboards to communicate results. I don't know if you know HTML widgets, like these are JavaScript libraries, like we have seen Leaflet, but there are others. Diagraphs for time trends. Plotly is just taking the ggplot, and you can do it interactively with these data tables to show tables where you can order the columns or search a value. So these are HTML widgets. You can also, with R, write reproducible documents with R Markdown. So R Markdown can be used to turn our analysis into fully reproducible documents that can be shared with others, and you can use HTML, PDF, or Word. Who has used R Markdown before? So many of you. So you have the header where you put your information. Then the text is written with Markdown syntax. So if you want bold text, you put it into stars, italic text. You can put lists. And then you have chunks with R code, with the R code to be executed. And then there are several options if you want to show the code in the document or not, or the results. And then, yes, you write a R Markdown document, and then when you compile this document, you will get a document with the text, with the formatted text, and also with the output of the R code. You can also create interactive dashboards with Flex Dashboard. And this is useful to publish a group of related data visualizations. So this is written with Markdown as well. So first you need to specify a layout where you have the number of columns and the number of rows. And then, so you specify, for example, here I have 2 columns. The first column has 1 row and the second column has 2 rows. In the first column, I can put one plot, and the other column I can put another plot and another plot. And this is one example. For example, this shows air pollution globally. And here I have done, a leaflet map, a data table, and then a ggplot. And you can also do it interactively. So you can, for example, here on the left, I have a filter where the user can filter values and show like values greater than 12, for example, and it will filter the values. You can also write Shiny web applications. Shiny is a web application framework for R that enables to build interactive web applications. For example, I wrote one Shiny app that is called Spatial API app for disease risk estimation, cluster detection, and interactive visualization. And here the user can upload the data, can upload the map, and then by clicking some buttons, they can obtain disease risk estimates using INLA, and also detecting clusters using scan statistics in the scan software, and then they can visualize the data in an interactive way. Who has used Shiny before? A few of you. So Shiny is a directory. Well, it's an R file with 3 components: the user interface, the server function, and then a call to Shiny app using the user interface and the server function. And then you write this R file, you save it, and then to run the app, you just call library Shiny, run app, and you put the directory of the R file, and you can launch the application. You can put several inputs like buttons to do some actions, date inputs, numeric inputs, sliders, and then you can show information using plots, tables, images, text. So this is what you need to write. So in the R file, you write the user interface and the server function. Or you can also have 2 separate files if your Shiny app has a lot of code. So in the user interface is what the user is going to see, and you include inputs and outputs like these inputs or these outputs. And then in the server function, you put the code to build the output. So if, for example, I have an input, a numeric input, so the user can enter a number, and each time the user enter a number, the plot changes. So we call this input my input, and then we say output my output is render, and here we put the code to produce the output, and if this code uses my input, each time the user changes the input, the output will change. So for example here, this is a Shiny web application that shows a histogram computed with the number of observations that the user introduces in this numeric box. Like, let's see if it works. So here, if I change the number, if I put 10, the histogram changes, or if I put 3,000, the histogram changes. And here you have the user interface that has a numeric input, that is this number, and the output, this plot, and then the server function that is, has the code to produce this plot. And then to share the signing up, you can do two things. You can send all the files to the other person that wants to use your Shiny app, but they need R, or you can host the app as a website at its own URL. And here I have a tutorial in case you are interested in seeing an example of how to create this interactive visualization, this Flex dashboard. And finally, as I told you this morning, I'm joining KAUST, and if you are interested in joining my group, please let me know, and I will be very happy to discuss the details of these positions. I have openings for PhD students and postdocs. And that's it.